Hi everybody, welcome to another video in Pre-Calculus, section 4.3, Exponential Functions. First, evaluate exponential function. So let's just evaluate this 3 to the 1.7. So just do this and I'll get to the point later. So that is about 6.473. Right, next 1.73. Six point 6899, and now 3 to the square root of 3. And we have that. Right, so I just get a few decimal places. Now I get back to the point of this example later, but now just go to some properties of the exponents. Let S, T, A, and B are real numbers. In addition to that, let A and B be positive, and A and B will be the basis of the exponent here. So anything raised to 0 power is 1, and that is except this is 8 is greater than 0. If we have 0 raised to 0 power, if we put that in the calculator, it says undefined. So we want to have something greater than 0, and that if anything greater than 0 raised to 0 power is 1. 1 raised to any power is 1. That S can be any number. There's no restriction here. Could be 0, could be any number, negative, positive, anything. Now, if I have A times B to the S power, it is the same thing as A to the S and then B to the S power. Yeah. The difference between that properties and this property is that this one we have one basis, this one we have two different bases, right? And then when we multiply two things with the same basis, which is add the exponents, if we divide, we will subtract, and we have another power, we just combine the powers. And now when we have a negative exponent, it is like 1 over the same thing but to the positive exponent. So what we do here is let's say like that. Now if we move that to the bottom, that becomes negative. So that's what I would say, cross the line, change the sign. Right. Now this, when we have A raised to the T power under the root of the S order. So in this case what we have is T is on the top, T is the power will be on the top, and S is the root index of the radical, or the root will stay at the bottom. So that's why we have those properties, right? Now with this we go back to the purpose of this exercise. So think about this. If I ask you what is 2 square, let's just keep 3, right? Okay, 3 square, 3 times 3, right? So that is 9. 3 cubed, 27. So that's good, right? Now how about 2 to the 2.5? Of course it's not going to be in between those numbers. It is in between but not in the middle. So what we have to write this as 3, 2.5, we can write that as 5 halves. And then with this we can say 3 power on top, root at the bottom. We can do 3 to the 5th power, and then we can take the square root, so we can get some values, right? Of course, then we can do for any decimal places like 2.4 or 2.45 something. We can write this as a rational number, and then turn that into the root and power, and we can evaluate, right? So that's the point. The point here is, if you see square root of 3 is 1.732 something, so we can just say 1.73, and we can go to 1.73, and the point here, when we try to evaluate 3 square root of 3, we'll estimate that as that number 3 to the 1.732, and for a rational number we can write that as the power and root, and we can estimate. So with that we can evaluate any power, right? So that is the exercise here. We're not just, of course the calculator can do that, but back in the time when there's no calculator, that's where we can evaluate. We can show that we can evaluate an exponential to any exponent. Of course, then we say, how do we do the square root? Well, that's a different story. Right. Next, exponential function. We define exponential function with a coefficient c here. That is not equal to 0. Where a is the positive real numbers, and just like what we had before, a, we don't want the base to be negative, but in addition to that, we don't want the base equal to 1, because that's simple. If we have the function 1 to the x, it doesn't matter, right? Because 1 raised to any power is still 1, and we just have a constant, so it's not really interesting. So we want the function not to be a function, not a constant. We want that function we don't want that function to be a constant, so we make the base positive and not equal to 1. And then c, we don't want that to be 0 either, so we choose c not equal to 0. And in this case we have a is the growth factor, and then c is the initial values when x equal to 0. Right. 2. For exponential function in this form, see, we have the function in this form, a is positive and not equal to 1. If x is any real numbers, then the ratio of f of x plus 1 over f of x is equal to a constant, a, which is the growth factor, or we can write like this. Now, so let's look at this example. Determine whether the following function is linear, exponential, or neither. And for those that are linear, find the linear function. And for those that are exponential, find the exponential function for tomorrow. So what we have in this case, if we try to plot them, we can see if it is a linear function, exponential function, but we use the theorem. Now, what we do is simple. We just look at the number 6, 2, -2, -6, and -10. Do they increase by the same number, or do they multiply? How do we get from this number to the next? So what we see here is, to get to this number, from this number to the next, we minus 4, right? So that means what I can write like this is the function of x plus 1 is equal to the function at x minus 4. Yeah. The next one is equal to the previous one minus 4. That's what we have. Because of this is not exponential function. It is a linear function. So we increase at the same time. So we can say we start here from 0. When x equal to 0, y equal to 2, and that's where we start. So I know this is when we study this, we skip a few sections, and one of those sections are linear functions, so we don't really have that part. But so there's a linear function, and we have the slope. So we take any 2 points and we find the slope. Let's choose I choose this set of points. Y2 is -2, x2 is 1, y1 is 2, x1 is 0, so we have -4. So that is the slope. Remember that on the section when we find the equation of the secant line, that's exactly what we have here. And then we have y minus y1 equal to m x minus x1. Then we have y minus y1. I can just pick any of this set of points. Let's just pick this point. It's 2 equal to the slope. x1 is 0. Right? So if y minus 2 equal to minus 4x. So plus 2 on the other side. So y equal to -4x plus 2. Right. So that is the equation of a line. I remember what we did here is way back in the section where we're trying to find the equation of a secant line, where we know all the point lie on the same line. So we just take any 2 points, we find the slope, and then we can find the equation of a line. So that's what we have. We know that it is the equation of a line because the difference of consecutive, f of x plus 1 and f of x, the difference is just -1. If x increased by 1, y decreased by -4. That is the constant, -4. Right. Now, on this one, how do we get from this to the next? How do we get from this to the next and just keep doing that? Right. So, by the way, we cannot subtract anymore. What we can get from this to the next, what we actually do is divide by 3. Or multiply by 1/3. Right? So if x increase by 1, y will multiply by 1/3 to get to the next values. So we'll write f of x plus 1 equal to f of x. The next value is equal to this values times 1/3. Because there's a constant like that, so this is the exponential function. So exponential function, that means it's going to be f of x equal to c a to the x power. And the a is easy to determine. That gives us a. And then the c here is the initial values. Initial values That is when x equal to 0. So that gives us c equal to 27. So bottom line is the function is 27 times 1 over 3 to x power. And then we can check. When x equal to 0, 1/3 to the 0 power is 1 times 27 is 27. And so far, so that's what we have. Yeah. So that's the difference between the exponential function and the linear function. Exponential function, if we x increasing by 1, y will be multiplied by a constant. So that's what we have. Right. Now let's graph some exponential function. Now we just, if we don't know a graph, we just plug in the points, pretty much. 3 to x power. Right. So what is 3 to the negative 2? Now we just get familiar to the properties we have earlier, right? 3 to negative 2 is 1 over 3 to the second, simply because cross the line, change the sign from negative to positive. That is 1 over 9. 3 to negative 1 is 1 over 3 to the first is 1/3. 3 to 0 power, anything to 0 power is 1. 3 to the first, anything to the first power is itself. 3 square is 3 times 3 will be 9. So I have those points. Right. X equal to 0, y equal to 1. X equal to 1, y equal to 3. X equal to negative 1, negative 1/3. And then 2 will be 9, will be way up there. So we have the function y equal to 3 to the x look like that. Right. Next, of course, then after this we will see the characteristic of those exponential functions. But for now, let's just plot in the points. Let's just plot the points. Right, 1/2 to the x power, 1/2 to negative 2. That's we have 1 to negative 2 over 2 to negative 2. Right? Ratio that power, so that power goes to the top, goes to the bottom. Now, cross the line, change the sign. 2 square goes on top, 1 square goes at the bottom. That is 4 over 1 is 4. 1/2 raised to negative 1. 1 to negative 1. 2 to negative 1. Once again, cross the line, change the sign. 2 to the first power on top, 1 to 1 at the bottom. So 2 over 1 is 2. 1/2 to the 0 power, anything to 0 power is 1. 1/2 to the first, anything to the first power is itself. And 1/2 square, the square go to the top, go to the bottom. So we have those points. Right. 0 is 1. X equal to 0, y equal to 1. Negative 1 is 2. Negative 2 is 4. 1 is 1/2. 2 is 1/4. So we have y. So that is the function y equal to 1/2 to the x power. Right. So one thing that we see that are common of those two, both of them will have the point 0 and 1, right? Because it doesn't matter what the base is. anything raised to 0 power is 1. So we have a to 0 power is 1. So that gives us the common point here. So always go to that point. Next, the base is positive. Doesn't matter what the exponent is, the function cannot get below the x-axis. So in that case, we have the horizontal asymptote is y equal to 0, or horizontal asymptote y equal to 0. So y will go to 0 as x go to infinity here, and y go to 0 as x go to negative infinity there. But bottom line is, cannot get below the x-axis, and y equal to 0, or the x-axis is the horizontal asymptote. And one more thing, this is the base that is bigger than 1, it is increasing. The base less than 1, it is decreasing. I put all of those properties together in the table. We have this exponential function. Now we just ignore the c in front of it. Now the domain, all real numbers. The range, positive numbers. Right, and this is what we said earlier. There is no x-intercept because the function is positive. It cannot get below the x-axis, so we will not intercept the x-axis. So there's no x-intercept. There will be the y-intercept 0 and 1. That's simply because a to 0 power is 1. So when x equal to 0, y equal to 1. That's what we have. Y equal to 0, or the x-axis, is the horizontal asymptote. And if it is greater than 1, increasing. If it is greater than 1, it is increasing. If it is between 0 and 1, it is decreasing. Notice that exponential function, the base have to be positive. So we don't have the case less than 0. We only have greater than 0 and not equal to 1. So it could be between 0 and 1 or bigger than 1. Those are the only possibilities. Right, and the graph. No, this is easy. When a equal to negative 1, we have 1 over a. So the graph goes through this point. And finally, similar to the graph of polynomial function, exponential function has the graph that is smooth and continuous. So there's no corners, no gaps. Now with that, how do we sketch some exponential function like this, just based on transformation? So f of x equal to 2 to the x minus 3 plus 1. So first of all, if we look at the basic function of 2 to the x, 2 to the x is when x equal to 1, x equal to 0. So 2 to the x will look like this. So that is the basic function, right? So to graph exponential function, we need two things. First, the point 0 and 1, and then the horizontal asymptote. Now what we have is minus 3 and plus 1. So minus 3 to the x, meaning that will move 3 units to the right. And plus 1 will be 1 unit up. Yeah, based on that function. So pretty much we have this point 3 units to the right and 1 unit up. And the line, the horizontal asymptote, 3 units to the right, still the same line, and 1 unit up. So we have this line, and then we just have that function. Two to x minus 3 plus 1. So that's what we have. Just based on the transformation. Right. Now let's sketch this one. So the previous one we have 2 to the x, the base is bigger than 1, which is increasing. Now this one, the base is 1/2, which is less than 1, so it is decreasing. So first we look at the graph. Y equal to 1/2 x, 1/2 to the x power. By the way, in relation to that previous one, how do we graph that? Okay. Now let's just look at, so we have this, y equal to 2 to the x power, look like this. Now in relation to that, what is the graph of 1/2 to the x power, right? Let's see. Y equal to 1/2 to the x power. That means we have 1 to the x power over 2 to the x power. Now 1 raised to any power is still 1. 2 to the x from the bottom. Now from that, if we move to the top, cross the line, change the sign, 2 to negative x. So the graph of 2 to the x and 2 to negative x, pretty much we change the sign of x. Therefore, what we have is a horizontal reflection, which I could draw better than what I'm going to. Yeah, so just a mirror image on the other side. So it's y equal to 2 to negative x, or we can say 1/2 to the x power. Yeah. So indeed, the 1/2 to the x power and 2 to the x power should be the mirror image on the y-axis, because that is a horizontal reflection since we change the x to negative x. Right. So that we have, yeah, just do mentally. Earlier we have 2 to the x is 2 to the second power is 4, so from here just switch to the other side. Right, so we have that graph, and then of course the horizontal asymptote. Now what we have in addition to that, +1, -1, and with the negative sign here. So this negative sign is the reflection, vertical reflection. But before that we have the +1, +1. That is 1 unit to the left, because that's what we add to the x. And then the -1. Here, which is 1 unit down. So those are the transformation, but in what order do we evaluate this? So actually, first the x values we add to the x value, so that is actually the first thing we do. So the first transformation is move this 1 unit to the left, and after that reflection, flip it upside down, and then after that move 1 unit down. So those are the orders of transformation. So first 1 unit to the left, that is that transformation, and then flip it upside down, finally 1 unit down. So it will be that. Of course, we can confirm this with the graph. Negative 1/2 or 0.5 to the x plus 1, and then minus 1. Yeah. See, there's a we have this point when x equal to -1, y equal to 2. Yeah. So that's what we have. Right, so that's what we have. Just using transformation to graph. Next, we define the number e. So this is the second most common constant, second to pi, because pi is the most famous constant. E is the second. Right. We define e as this expression as n goes to infinity. So that is pretty much limit when n go to infinity of that is equal to 2.817. 2.8. Actually, I memorized that number. It is not this. Sorry, I changed that. I type it and it is not right. So 2.71828, 1828, and then 45, 90, 45. I think. Yeah. Sorry. Not that. It is. That, of course, how do we come up with this number? Of course, we just do this, and it will take that, let n goes to infinity. So let's say it. I could say 1 plus 1 over, let's use x instead of n to the x. Right? Now, let's evaluate that function at 10. When x equal to 10, with that number. How about 100? That. Of course, we will let x goes to infinity. The bigger number we choose, the closer that expression close to this. So of course we can let x to be very big number. Essentially, that will equal to this number. Right. Next we have exponential equation. Later on in the chapter we have different type of equation, but here we only have something very basic. How do we solve this equation? 9 to the 2x minus 5 equal to 27 to the x power. They will say 9 and 27, both of them can be written as base of 3, right? So 3 squared, 2x minus 5, and 3 cubed is 27. Now, two things, power, and then we have another power. We will multiply these exponents. So 2 to 2x minus 5 equal to 3 to the 3x. Right? Now, two things are equal. The bases are equal. The exponent are equal. That's exactly what we use here. So in that case, we have 2 to x minus 5 equal to 3x. So just let the exponent be equal to each other. Here we have 4x minus 5 equal to 3x. Subtract the 3x on this side and add 5 on the other side. We have x equal to 5. Right? Subtract 3x on the other side, we have x, and add 5 to the other side, we have 5. So x equal to 5. And put it back in here, we have 5. 2 times 5 is 10 minus 5, so 9 to the 5th power is equal to 27. Of course, I forgot to multiply this out, right? By 10. Sorry. Right. So 2 times 10 is 20 minus 5, so 9 to the 15. Should be the same as 27 to the 10. Yeah, so those two numbers are equal. Right, next. Here we have 4 to the x plus 2 and then 8 to the x. 4 and 8, both of them are power of 2, right? So we try to change them to the same basis, because when the bases are equal, the exponents are equal. So we can write 2 to the second, which is 4 to x plus 2. And then a to the x will be 2 cubed to x power. Now, power to another power, we multiply this 2 and x plus 2. And then here we can say 2 to the 3x. Multiply the exponent. Next, cross the line, change the sign. Move that from the bottom to the top. Now two things are equal, the bases are equal, the exponent will be equal. So 2 and 2 cancel out, we have 2 times x plus 2 equal to negative 3x. Multiply it out to x plus 4 equal to negative 3x. Okay, I add 3x to the other side. And minus 4 to the other side. So we have 5x equal to minus 4. With that, give us x equal to negative 4 over 5. Right. So, of course, we can put it back and check. 4 raised to the power of negative 4/5 plus 2. Then 1 over 8 to the negative 4/5. This would be the same. Right. Right. Next, we have this. E to negative x squared is equal to this one. First, let's try to simplify this. On the left hand side, e to negative x squared. On the right hand side, power to another power, we can write this as e to the 5x. E to the 6 from the bottom, move to the top. Cross the line, change the sign, change to negative. Multiply together, we can combine the exponent. Now two things are equal, the exponent will be equal. So here, let's just move everything to one side. Right. Now, x squared plus 5x minus 6 look like we can factor. Since this is negative 6, one of them is negative, one of them is negative. It is x, so we should have x plus something and x minus something, because they have to multiply to negative 6. And add up to 5, so more likely 6 and negative 1. So those are the factors. And then we let each factor equal to 0. Of course, if you don't want to do this, you can use quadratic formula. Either way, quadratic equation should be simple. Right, here we have x equal to x plus 6 x minus 1 equal to 0. So x plus 6 equal to 0, x minus 1 equal to 0. So x equal to negative 6 and x equal to 1. Right, so that's simple enough. So we're trying to change the equation to have the same basis on both sides, because when the bases are the same, the exponents will be the same. Because the exponential function, it is a one-to-one function, 1x, 1y. So in that case, when we set the whole function equal each other, then the x's have to be equal. The exponent have to be equal. Right. Here an example, an application problem. Suppose between 9 and 10 p.m. a car arrived at the drive-thru at the 15 cars per hour. So we can write at that 0.25 car per minute. The following will give from statistic will use to determine a probability that a car will arrive within 10 minutes of 9 p.m. So determine the probability that a car will arrive within 5 minutes of 9 p.m. That is between 9 and 9:05. So in here in the equation we have t is in terms of the minute, and we're just going to put directly in this equation. So pretty much what we do is f of, we put 5 in for t, one minus e. Either we use this button, we have e to the x already, or if we use this button, then we have to enter the power. Either way. Two 5 times 5, and we have 0.7135. Yeah, 4 decimal places. Let's say that. Right. Determine the probability that the car will arrive within 30 minutes of 9 p.m. Meaning that the probability that the car will arrive between 9 and 9 p.m. 9 and 9:30. We're going to put 30 in for t. And we have 0.999. And it will say, by the way, this is almost 100%. Almost 1, which is 100%. So does that make sense? Right, so we're talking about the car at the drive-thru. And we know that typically in an hour between 9 and 10, we have 15 cars. This probability meaning that within the first half hour, almost certain, because that is close to 1, right? 99.9%, which is almost 100%. So very close to 100%. So we can say that within the first half an hour, the probability that a car arrives at that point is 99.9%. Once again, within the first, from 9 and 9:30, the probability that a car will arrive is 99.9%. Think about this. If we have 15 cars kind of randomly go through the drive-thru from 9 to 10 p.m. in the first half an hour, 99.9% of them, one of the car have to go through it. Does that make sense? Does that look reasonable? Does that sound reasonable? Yeah. So, and it should be reasonable, because if the car randomly go from 9, and then will be 15 cars go randomly from 9 to 10, then the probability that one of them will go in the first half an hour is quite a lot. Because if it's not happen, that means in the first 30 minutes, none of the car will go through the right through. And that would be very rare. Right. So, now, if we have this probability and this probability, if we just subtract them, then we have the probability that the car can go from 9:05 to 9:25. Right. Anyway, let's just, if we want to sketch the graph, it's easy. We have exponential function. Look like that. And now we have a minus a negative number multiplied to it. So we'll flip to this sign. And then with the negative, if we flip, and then plus 1. So bottom line is when we put all of the graph, all of them together, when t equal to 0, e to 0 power is 1, 1 minus 1 is 0. So when t equal to 0, e to 0 power is 1, 1 minus 1 is 0. So we have this function. So the graph will look like this. The horizontal asymptote is 1. So when you get close to, when t get very big number like 60 minutes or higher, this will get closer and closer to 1. But when t equal to 0, it is 1. So we have the graph like this. Now just get used to how to have the exponential function in the application. Of course, we have a lot more application later on. But that's what we have in this section. Pretty much the property of the exponents. These properties. And we studied the graph of exponential function. We have this characteristic go to the point 0 and 1, the domain and range, domain all real numbers, the range positive numbers. The x-axis is the horizontal asymptote, and after that we show the exponential equation, the first type of exponential equation, where we let the bases are equal, then the exponent will be equal. And that's all we have for this section. As always, thank you for watching, and see you in another video in pre-calculus.